This is Shiva from the Camel team at Calico. Today I'll be talking about our work titled Find Your Microenvironments Faster Using Spatial LDA. This work was done in collaboration with my colleagues Jun and Zhenhao. Spatial organization of different cell types in tissues have been shown to be important factors in many biological processes such as aging and cancer. In particular, organization of cells and tumor microenvironment has been shown to play a crucial role in treatment response, disease pathology, and patient outcome. As shown here as an example, if we consider these two spatial profiled images, even though the proportions of different cell types are the same in these two different images, one type of spatial organization might be good for patients than the other. Spatial LDA is a general-purpose probabilistic model that has been used to discover novel microenvironments in settings such as triple-negative breast cancer and tuberculosis infections. As an example, proportion of tumor cells in a topic 4 microenvironment identified by spatial LDA was found to be strongly associated with poor survival in triple-negative breast cancer patients. Here is the outline of my talk. Firstly, brief overview of spatial LDA, identify scalability issues with spatial LDA, our proposed solution, and results. Spatial LDA models identification of microenvironments from multiplexed images as a topic modeling problem, where groups of microenvironments are analogous to groups of documents, a single document is analogous to a microenvironment, and the vocabulary to the cell types. One can think of in situ profiled image to be a graph with vertices representing microenvironments and edges connecting neighboring microenvironments spatially. Spatial LDA adds a Laplacian constraint over every pair of alphas that are connected by an edge. Intuitively, this graph defines neighborhoods that should have similar topic distributions, and sigma of Laplacian distribution controls how strongly that inductive bias is enforced. Spatial LDA uses mean field variation inference for learning the parameters, and it involves optimizing a non-smooth function for the variational parameter eta due to the presence of the Laplacian prior. Efficient parameter learning was carried out by ADMM plus primal dual interior point optimization approaches, but these optimization steps do not scale well with the number of data points compared to gradient-based optimization methods for training modern neural networks. So the objective of this work is to neuralize spatial LDA and thereby training it faster. So we turned to autoencoding variational base for training spatial LDA, but since Dirichlet and categorical distributions are not readily reparameterizable, we took the following approach. Since spatial LDA is a generalization of classical LDA, we took ideas from autoencoding variational based version of classical LDA proposed by Srivatsava and his colleagues and added spatial regularization similar to spatial LDA. Here is our proposed neural spatial LDA. As suggested by Srivatsava and his colleagues, we marginalize out the discrete latent variable z's in our generative model of spatial LDA, and we approximate Dirichlet distribution with logistic normal with diagonal covariance. Logistic normal could be easily reparameterized as shown here. Then we add a spatial regularization to the posterior means of microenvironments that are connected via an edge, similar to the Laplacian prior in spatial LDA. Our final objective looks like this. We first showed neural spatial LDA captures similar microenvironments as spatial LDA in 3 different datasets colored by their most probable topic, with the left being simulated data. Second, since spatial LDA is a probabilistic model, each cell gets a distribution of topics it belongs to. To measure how well the topic distributions of cells correlate between spatial LDA and neural spatial LDA, we take random pairs of cells and compute the KL divergence between the topic distributions and report their rank correlation. As shown here, even the topic distributions of cells have high correlation between these two methods. Finally, here we show the training and inference timing comparison between spatial and neural spatial LDA. As shown here, on an average, we get 20x speed up in training and inference timings. In summary, spatial LDA is a general-purpose probabilistic model to identify microenvironments in an unsupervised way in spatial profile data. Its inability to utilize GPUs or TPUs and slow training and inference limits its use in large data domain applications. We convert spatial LDA into a encoder-decoder style network, which we call neural spatial LDA. We verify both qualitatively and quantitatively that we could recover similar microenvironments as spatial LDA using neural spatial LDA on 3 different datasets. On an average, we achieve 20x speed up in training and inference timings. Most importantly, neural spatial LDA opens up doors to incorporate supervised signals when available to identify microenvironments, which we are leaving for future work. Thank you.